Hello, I'm Aditya Sengupta. I'm a master's student at the University of Cambridge, and today I'll be presenting the work I've been leading at the UC Santa Cruz Lab for Adaptive Optics on the linear quadratic Gaussian method for tip-tilt control. So our research aims are to demonstrate LQG control in tip-tilt in the lab with the fast setup, which is the focal plane wavefront sensor, and also to examine several parts of the model to see where there's room for further optimization on top of previous implementations, such as the one on the Gemini Planet Imager. In particular, one that I'm interested in is incorporating the hardware dynamics, which is to say, if we steer the deformable mirror to a certain position, will it get there instantly? Will it take some time? Will it go through some intermediate states? And how can we leverage all of that information to do better control? And additionally, I am trying to make all the code I write as generalizable as possible so that it can be applied to future control experiments to run more complicated control algorithms, for example. So it's also building a common infrastructure for control experiments on SEAL and using FAST in particular. So I'll start by explaining the general concept of LQG control, which is if we have some dynamical system with a known update rule, which says from this position, you will move to this one, for example, and we combine that with information from sensors, which says you're here, with a different source of uncertainty, we have two sources of information, and we can combine those two sources of information to get an optimal position somewhere in between, in this case over here, which you see visually by overlapping these two covariance ovals in XY space. So because these sources of information are independent, we can combine them and you can get a better estimate than you could from either one alone. And this process is known as Kalman filtering. And when you use a Kalman filter to predict what's going to happen in the future and control those future states, that's known as linear quadratic Gaussian control. To apply that, we need a physics model that accurately describes the problem that we're facing with tip-tilt control. In this case, we're using a common approach, which is to separate it out into two components, atmospheric turbulence and vibrations. And we identify both of those through the open loop power spectral density, shown over here, originally in blue and then overplotted in orange. And we look at two particular components of that. One are these vibration peaks, and another is the general trend line, which is a linear fit in log-log space to describe a power law. And so the vibration peaks describe some sort of physical vibration going on the bench or on the AO system in general. And the linear fit describes the dynamics of the turbulence. So both of these are modeled individually by autoregressive processes, and you can combine their state transition matrices in just a block diagonal form to make an overall model that's the sum of these individual models that we can use for prediction or correction. And one of the other things that I'm looking to add to this is, as I said, the plant model. And we can see here a little more visually what that means. So in this case, we're telling our system to go from this position 0 to position 1. But in reality, it won't perfectly mirror that because of the dynamics inherent to telling hardware to do something. So what you'll actually see is something like this. It goes smoothly from 0 to 1, and it takes some time to do that. So it's the rise time, and once it's reached there, it'll overshoot by a bit and then come back down and then eventually settle into the correct position. So knowing something about these dynamics, quantifying it and putting that back into the model that we just saw and adding those as extra terms will potentially help us quite a bit with our control. So having set up everything we want to do, let's look at how well this works. First, in simulation with 3 vibration modes that we see over here in the open loop PSD, there is a dramatic difference. So over here we have the open loop simulated RMS error in blue, and the result of integrated control in orange, and way down here we have the LQG control residual. This is a bit more dramatic than you would get in reality because it's in simulation, everything's idealized, but it gives you a sense of the power of knowing exactly what the dynamics of the control problem are. And the fact that LQG is somehow exploiting the structure of the problem to do this is borne out by looking at the transfer function here. So with the open loop PSD, we have these peaks that are completely gone in the closed loop PSD because it's able to leverage that information. It's able to leverage the fact that it knows there are these vibration peaks here that it has to correct. And you see these dramatic dips in the rejection transfer function, which is just the ratio of the two of these. that says it's discovered that there are these vibration peaks, it is correcting them appropriately, and it's got the best performance it can possibly get. So this is how it works in simulation, and this is encouraging enough that we can move on to lab demonstrations. So in the lab, we have a few steps. The first one is for system identification. We put on some simple patterns such as unit steps and sine waves, and eventually the full simulated turbulence plus vibration signal that we'll be trying to correct. And once we have a model of that and a model of what happens when I give the specific input, what output should I expect, I can then start looking at closed loop control. In our case, we're doing this by driving the DM to specific known positions that correspond to, say, one of those vibration peaks or a specific characterization of a kind of turbulence. And then we run in parallel a closed loop controller on those known disturbances to see the impact of correction. And once we have that closed loop control running, we can change the algorithm. We can go from integrated to LQG. You can change the parameters within the algorithm. You can add more terms and fewer terms for more vibration peaks or different kinds of turbulence, and see the effects of misidentification of the system and experiment with it from there. So over here is the lab setup we've been using, and this is a quick video of the camera display. So you see that it's running at 100 Hertz, which is what it's been, which is the frame rate for all of the plots that I'll be showing here. So before running any of these experiments, we do a few calibration steps. One of these is alignment, which is to find the best flat position that provides the optimal contrast for actually being able to sense these tip tilts using the focal plane wavefront sensor. And from an aligned position, we make interaction and command matrices, by which we mean we apply some pure Zernike polynomials. Only tip tilt is significant. We've done up to the first 5 modes over here. We observe the response and we invert that so that whenever we get an image, we can essentially project that onto the ideal responses and see which components of the ideal Zernikes are in the image that we just got. And we can look at those in a linearity plot, which is essentially on the x-axis, there is an applied disturbance, and on the y-axis, there is a response in each mode. What we want to see, and what we indeed do see over here, is the one that we're varying should be pretty close to this dotted line y equals x, so that if I put on a disturbance of x, I get an output of also x, and that the rest of the modes are relatively flat, so that there's very little crosstalk between them. If I'm perturbing tip, I don't necessarily want to be moving tilt. And we see quite a large linear range for both of these, so this is encouraging, and we can move on. Now, earlier I mentioned that we'd be doing the applying disturbances and correction in the loop in parallel. And this code base is in pure Python so that it can be easily extended, and because the interface to the hardware is also in Python. And getting Python to do something in real time is quite difficult. So the strategy we're using uses the Python multiprocessing library along with the technique known as spin locking, which is essentially staying stuck in a dummy while loop until a specific event happens. And we make use of that so that things happen on a set schedule and they don't drift. So we're running at 100 Hertz, which means we run 0 to whenever the loop ends, and then we spin lock until time 0.01. We run until whenever the loop ends, spin lock till 0.02, and so on, so that we don't have drift over time and things actually happen when we say they'll happen. This is very important for a state space model because everything depends on the underlying model moving forward only 0.01 seconds when the loop moves forward that much. So we run with these in parallel. Over here, the commands are pre-computed and we apply them at specific times. And over here in the loop, we get an image, we measure the Zernikes from it, and we feed those into a control law, which could be just any function that takes you from the Zernikes to the DM command. And we apply the DM command. And so this works perfectly in parallel. And we can actually test control algorithms with not much overhead this way. And we can see that visually as well. This is a representative schedule of experiments here. So over here is the start of the control loop where we get an image. Here we take a measurement, about half a frame of delay there. And almost instantly after that, the LQG optimal control command is computed. And you see that everything happens within the same frame. So you don't have any significant lag unless we want to induce it for testing purposes. And we don't have any going out of sync. You can also see that in these histograms here, which shows once again that there's not much of a frame delay. So what did we find? First of all, we got bench results from the integrator, which show what we would want. From that, once you drive it to a certain point, it's driven back down relatively quickly. And applying a sine wave causes a much smaller sine wave without the out. And we were also able to run system identification. A first order model seems to give the best fit, but this is still an evolving part of the research. And finally, another evolving part of the research is actually putting all of this together and getting bench results with the LQG controller, which is not providing as dramatic an improvement as we expected, and sometimes notching out the peak and sometimes not. And this is an ongoing area of research, which is probably mostly caused by the synchronization errors that have since been fixed. And so I'm working right now on rerunning these experiments with the better synchronization that I described and seeing the improvement there. So in conclusion, we showed the efficacy and simulation of this method. We developed a real-time control infrastructure, and work is ongoing to show the efficacy of LQG on the bench. All right, thank you very much.